Hey guys, we're going to be talking about radioactive decay. It's one of my favorite topics, so we'll talk about the different types of fallout, and then I got a bunch of examples, and of course it's all at work, but I have video, so I can show you that. So we'll be looking at this stuff. And radioactive decay is a naturally occurring process. There's a lot of neat things that we can discuss, and so I'm just fiddling around with something that I've got here. This is something that y'all are going to fiddle around with when you get to the lab, and this is just something that naturally occurs in nature, and it's pretty neat. There's some neat examples. This is a thing that does happen. You know, I just found this recently. This was 13 hours ago. So this kind of stuff is always in the, seems like there's something always in the news about activity and fallout. I actually have some radioactive sources that I use in class, and of course I was going to use in class if we were in class, so I've got these little discs, and you can actually purchase these. They're not harmful in the sense that they can't be dispersed into the air, but you really don't want to just carry them around in your pocket because they are actually radioactive. There are three different types of radioactivity: alpha, beta, and gamma, and so I have actually I have a number of different sources now of different alpha, beta, or gamma particles. So I did this in class. This is a little video that I shot with one of these things, and this is my little Geiger counter. And of course it's all at school and you can't go to school, but anyway, the Geiger counter just started going crazy. This is the little source sitting right underneath it right there. And there you go. So if you come across anything that's radioactive, then it'll produce this type of response from your Geiger counter, which I think is pretty cool. Now, of course, we are all impacted by radiation. Of course, there is a certain amount of what we call background, and you absorb that every moment of every day. And it's pretty normal, and it's not really going to hurt you. There's a certain amount of radioactivity coming from things like soil and concrete and things like this. But if you've ever had any sort of medical procedure, then you've come into contact with a bit more radiation than normal. Although it's still safe as long as you don't do it every day. So MRIs, you'll get a little bit more. X-rays. That's a thing. So there you go. Sometimes you may not even realize that you're getting a bigger dose. So my wife and I took a flight once, and I took my Geiger counter. I asked the TSA guys, and they said it was fine, so I took it. And then once we were up at about 30,000 feet, I turned the thing on. I know the video looks kind of funky because it's kind of, it's not right side up. But we turned the thing on around 30,000 feet, and it started going crazy and making little beeping sounds. And you get this little red light also on the counter. And so I forget what it tops out at. We'll just have to wait and see. But it makes that beeping sound, and it's can get a little scary. And we were afraid of getting in trouble or alerting people on the plane that we were doing something. But anyway, you're getting a bigger dose than you normally would, and the reason is at 30,000 feet there's less atmosphere shielding you, and so you're just naturally going to come in contact with more radiation. So I think this thing topped out around 3 microsieverts per hour. All right, and then finally, I have an example of when you come into contact with things that you may not know are radioactive. I already did the plane thing, but my wife and I went looking through some antique shops, and I was trying to find things that were radioactive, and I thought it would be hard to do. And in the first 15 minutes, found several things that were. I just took my Geiger counter, was kind of real careful with it. Found this clock. And we also found some glassware. And the glassware, as you can see, is actually green because there's a certain amount of uranium ore in there. And so that's mildly radioactive. This sucker, I have a video I'll show you. So they used to paint the dials of these clocks with this radium paint that would glow in the dark, because that's how they got clocks to glow in the dark. And the problem is that it's radioactive. And here, let me get my video going and I'll show you. All right, here's my video of that clock. Get it going. Put the Geiger counter down next to this clock. And the Geiger counter just went up and up and up. It was amazing. So these old clocks are sitting around, and I wonder how many people have these clocks sitting next to their bedside tables, and they don't even know that they're radioactive. So that's a thing. But radioactivity is all around us, that's for sure. So I want to talk about this a little bit. See if I can make myself bigger. Okay, so we got 3 types of radioactivity or radioactive decay. First type is called alpha. Alpha particles. So what's going on here is that atoms, certain ones, can become unstable, and this is a thing. Okay, so here's a periodic table, right? And all these little numbers, right? Or, this is the periodic table is essentially assembled in order by number of protons. Let's just say, I'm not a chemist, and so as you go down the list, you're getting more and more protons, and you're cramming more and more protons in there. And at some point, you get so many protons all together, and remember, they're all positive, and they're all feeling a repulsive force. That those repulsive forces get so strong that that strong nuclear force trying to hold everything together can't do it. And somewhere around in the 80s, you start getting a breakdown where things can't stay together and things go flying out, right? So Rn right here, you've got radon there, and starting around here, and then, much past 84, 85, 86, I think it's 83 actually, 82 is lead, so just after that, you got so many protons that you get this breakdown, and then you get things that are naturally radioactive, and so they spit out little particles, right? See if I can make myself bigger here. Hopefully I'm big. So these are the types of particles that you'll see. First type is called alpha particles. It looks like a fishy, and essentially is a helium nucleus, and there you go. So here's my example. You have radium-224 that will break down into radon-220. And you get your alpha particle here. The math is very easy, and you chemistry folks, ignore this because you know what you're doing, right? Both sides have to add up to the same numbers. So on the bottom, this has to be, if this is 88, then these two numbers have to add up to 88. On the top, if it's 224, then those two have to add up to 224. So I like this because it has these very, very defined rules, and it's fairly simple. You have 2 types of beta. Most of the time we just see one. This is negative beta, and essentially this is an electron that comes flying out. What you end up with is it's a neutron that splits essentially. So my example is something called carbon-14, which surprises people. Carbon is usually, we're usually talking about carbon-12, and there's so much carbon-based stuff here on Earth. We all have all these different elements in us. But there are isotopes of very common things that they are radioactive. They may not occur very often, very much in nature, but they are radioactive. So here you got carbon-14, right? Turns into nitrogen, and then you get your beta particle. And so the math here, 7 minus 1 is 6. 14 plus 0 is 14. It works out. This weird looking thing that I didn't do a very good job drawing, that is called an anti-neutrino. Anti-neutrino. And this is another particle, virtually massless. They fly through things. Way back when scientists were doing the math, and they figured out that if you take this and you get these products, there was still something left over. They couldn't figure it out, and they came up with this idea of the neutrino, which we think is a thing, and I'm pretty sure that there are experiments going on to show that these things exist. All right, another type is called beta positives. And so essentially this is wacky. It's like an electron, but it's positive. They call it a positron. And here's my example of the mathematics. There's one more type, and it's called gamma, and there's really no math that goes along with gamma. Gamma is just high energy. It's not really even considered a particle, and it is very nasty stuff, and it will cause cancer, and it's really strong stuff. Okay. All right. Let me make myself bigger here. So we're going to, in this video, talking about half-life. There's two ways to do this. I'm just going to talk about the easy way first. I would have done this in class. So let's say we have a sample. It's a radioactive sample. Maybe it's carbon-14. We have a sample size, a certain mass, let's say 4,000 grams, right? So the way this would work is the easiest thing to do would be to say, all right, what is the half-life, right? This is the time it takes for half of a sample to decay. And essentially what would happen is it turns into something else, right? And I guess I didn't mention it, but why do things do this, right? We talked about how all the protons are in the nucleus, and there are just too many of them, and it gets to be really unstable, and then it breaks apart, right? And it breaks down. What they're trying to do is it's trying to become happy. It's trying to become stable. It wants to become. It'd love to become one of the noble elements on the very right side of the chart, right? Essentially, most things after however many hundreds or thousands or millions of years will turn into lead. Lead is actually a very stable thing. So anyway, carbon-14 is going to break down. And so what happens is, I had to look this up, but the half-life for carbon-14 is around 5,800 years, give or take. So we'll just say the half-life is 5,800 years. Okay, so that's one half-life. And after one half-life, half of it's gone. So now you got 2,000 grams. There you go. And then you can just keep doing this. And you can say, okay, well, the second half-life, you only have 1,000 grams left. How long would that take? Well, 5,800 times 2 is around 11,000. And then you got the third half-life. Now you got 500 grams. 11,000, 17,000 something. Right. And then the fourth half-life, you get 250 grams. And at that point, I don't know, 23,000 years. Some of these things take a long time. There are a lot of implications here. We don't have the time. Now, one of the things about this is that, do you ever really get zero? And does it all turn into something else? And the answer is no. It's sort of a magic trick in the sense that it's sort of like jumping halfway, right? If I'm going to jump halfway to the wall, and I keep jumping halfway to the wall, will I get to the wall? I mean, the answer is yes. But if I actually truly try to jump halfway to the wall, will I ever really get there? And really the answer is no. And so what happens here is, it's going to approach zero, but it doesn't actually get there. And what you end up with is a function that kind of does that. But you get, never quite approaches zero, so it ends up being an exponential function. And that's how that would work. So, all right, so the half-life. I only have about a minute left. This is the easy way, right? I was just talking about this. Here's the equation that you can use, okay? This is the amount of mass that you would have to start with. This is the amount of mass that you would have left over after a certain amount of time. N up there is the number of half-lives. So that's how this works. Let me make myself small. Okay. So I have notes on this, and here it is right here. There's our graph. Now you can use a number of things here. Oops. You can make it mass. This equation can be used for mass. It can be used for number of nuclei. It can be used for activity. You can even solve for the number of half-lives. It's a very flexible thing. And there's examples in the notes. there you go.